In this lecture, we will study about electric potential due to a point charge. Suppose there is a charge Q which is placed at a particular point, and we have to find the electric potential at this point P, which is at a distance r from the charge Q. So according to the basic definition of electric potential, the potential at any point will be equal to the work done by the external force in bringing a charge of 1 coulomb from infinity to that point P. So suppose what we do is we go to infinity and take a charge of 1 coulomb, and slowly, this is a charge of 1 coulomb, and slowly we bring it here. Now as we bring it here, suppose it reaches a point A, which is plus 1 coulomb, and this A point is at a distance of x from this charge. Now when this 1 coulomb charge is placed at this point A, it comes at this point A, this charge Q, which we assume to be positive, it applies, it exerts a repulsive force F, which can be written as K Q 1 upon x square, which means F will be equal to K Q upon x square. But according to the definition of electric potential, we have to bring the charge in such a way that the net force should be zero. So what we do is, when we see that there is an external force acting along the positive x-axis, we ourselves will apply an external force along the negative x-axis, so that the net force of this charge of 1 coulomb becomes zero. So this external force has a magnitude equal to F. Now this F external will be equal to also K Q by x square. And in the next little instant of time, we will be moving this 1 coulomb charge a small distance dx. And when we will be moving it by a small distance dx, then the new distance between this charge q and this charge of 1 coulomb will be x minus dx, because distance is decreasing. But according to the convention, what happens is, even when the distance is decreasing, we write it as x plus dx. And while writing x plus dx, we say that dx is negative. Dx is negative. So now, as we can see, that f external is along the negative x-axis. Dx is also along the negative x-axis. So the work done by the external force in moving a small displacement dx, this work done, which we can denote as dw, this dw will be equal to F external into minus dx, because we have already have considered that dx is negative, into cos 0. So dw is equal to minus F external into dx. Now dw will be equal to minus, and F external I can write as kq by x square into dx. Cos 0 will be 1. So when I integrate this, I get the total work done. And I have to integrate it from infinity to the final distance was r. So I have to integrate it up to r. So w will be minus kq and integration 1 upon x square dx from infinity to r. Solving it further, we get minus kq, and the integration of 1 upon x square is minus 1 upon x from infinity to r. So minus and minus will make it plus. So kq, then 1 upon r minus 1 upon infinity. So w will be kq upon r. And as we already know that the work done in bringing a charge of 1 coulomb is equal to the potential. So the potential at the point P will be kq by r. So it means we can like summarize it. Suppose there is a charge q which is placed at some point, and there is a point P which is at a distance r. So the potential at this point will be kq upon r, where k will be 9 into 10 to the power 9, and the charge here can be either positive or negative. So we have to place this charge. I'll write a charge must be placed with sign. So let us have a look at this question. It says determine the potential at a point 0.5 meter. First is from a plus 20 microcoulomb point charge. Second is from a minus 20 microcoulomb point charge. Now suppose I solve the first part. So there is a charge of 20 microcoulomb which is placed at a distance, and the point P where we have to find the potential. The distance between the point P and this charge is 0.5 meter. So I have to simply apply the formula which we have studied. V will be equal to K Q upon R. Now if I try to solve it, so 4 into 9 I will get 36 into 10 to the power 9 plus 1 10, and 10 minus 6 is 4. So it will be 36 into 10 to the power 4 volts. This will be positive because the charge here is positive. When I solve the second case, I will see that there is a charge of minus 20 microcoulomb, and the point P is at a distance again 0.5 meter. So potential will be 9 into 10 to the power 9 into, now we have to write the charge along with sign. So it is minus 20 into 10 to the power minus 6 and divided by R. This R is 0.5. Again on solving it we get minus 36 into 10 to the power minus 4 volts. So the next question is also related to electric potential. They are saying what is the electrostatic potential at the surface of a silver nucleus of diameter 12.4 Fermi. Atomic number of silver is 47. So there is a silver nucleus. The diameter of this is 12.4 Fermi. Here Fermi means 10 to the power minus 15 meter. So the radius will be, if we divide this diameter by 2, we get 6.2 into 10 to the power minus 15 meter. There are 47, it is given the atomic number, which means there are 47 protons inside the nucleus. So the total charge inside the nucleus will be 47 into 1.6 into 10 to the power minus 19 coulombs. Now we have to find the potential at the surface. Suppose here there is a point P and this point is at a distance of R, which is 6.2 Fermi. So I have to simply apply the formula once again. The formula will be K Q, which is 47 into 1.6 into 10 to the power minus 19 divide by R. The value of R is 6.2 into 10 to the power minus 15 meter. So we will be, if we solve all of this, we will get 1.09 into 10 to the power 7 volts.